Hey guys, welcome back to my channel, and today we are going to study about difference between chromatic polynomial and chromatic number, and this is a part of graph coloring concept of graph theory. So let us try to understand this concept with a real life problem. Okay, the problem is like this. There are six subjects, okay, uh, a, B, C, D, E, F, A, B, C, D, E, F. Now the school wants to uh, create a timetable for the final exams of these six subjects, and any subject has been taken by three students. Okay, at least three students are taking uh, two subjects in common, like subject A and subject C. uh, there might be existing at least one student who is giving both the subjects final exams. So the school has created a graph where the edges represent, if there is an edge between the two subjects, that means that at least one student is giving both the subjects, so we cannot conduct the exam at the same day and same time. So the graph of the subjects where same student is giving at least the both the subjects is represented like this: A, C, okay, F, D, like this. I will remove the above writing, so I have more space to draw. Okay, and then a B, like this, E, subject E, and D. So this graph is representing, the edges represents that we cannot conduct exams of these subjects on the same day and the same time. So we have to schedule at least uh, two separate time slots for these subjects which are having edges between them. So the question is, what are the minimum number of time slots required? Minimum number of time slots required. Time slots mean different time, day and time for the exam. Time slots required so that the final exams, all the exams are conducted smoothly, and we require the minimum number, in minimum number of days we want to finish off the final exams. So how many minimum time slots required? That is known as the chromatic number of the graph. Chromatic number means given the constraints where the two nodes or two subjects which are adjacent cannot have the same colors. Let the time slot, different time slots are represented using different colors. Okay, so we cannot give the same color to adjacent nodes. Okay, so one such assignment of the time slots to this graph where minimum number of colors are used is the chromatic number. Okay, then we will see the chromatic polynomial as well. So how do we find how many minimum colors are required to color this graph such that adjacent nodes do not have the same color? uh, First we will write the degree of the graph. So why I am writing degree of all the nodes in the graph? Because there is a concept that a complete, if there is a subgraph of this original graph that has a complete graph, if I make for example K5, that is complete graph on 5 vertices, 3, 4, 5. So it will look like this. And then okay, so here you see how many minimum colors are required to color this complete graph on 5 vertices. If I give color this node color blue, I cannot use blue for any of the other 4 nodes because each and every node is adjacent to each other. So minimum colors required would be same as the number of nodes. This has to be colored different, red. This has to be colored yellow, for example. I cannot use the same color because all the nodes are adjacent to each other. The next will be a white color. The next would be maybe uh, 1, 2, 3, 4, 5. Okay, green I have to use, right? So there is a concept that the chromatic number of any complete graph is same as how many number of nodes are there in the graph. So let us try to find, is there any subgraph of this original graph that is a complete graph? Okay, then we know how many minimum colors would be required to color that graph. See, we will first find the degree of all the nodes. Okay, so here A has degree 3, B has degree 2, C has degree 1, 2, 3, D has 4, E has 2, right? And F also has 1, 2, 3, 4 degree. Okay. Now, which complete graph has a degree 4? All the nodes are having degree 4. It is K5, right? So, K5. So, can we have 5 nodes which are having degree 4? No. We have uh, uh, only 2 nodes having degree 4. So this cannot be, the K5 cannot be subgraph of this graph. So what is the next possibility? 3, right? What is a complete graph having degree 3? So that is equal to K4. Complete graph on 4 vertices. So do we have 4 vertices having degree 3? Yes. A, C, D, F. So here we can see there is a complete graph on 4 vertices. That means to color these, as these 4 A, C, D, F, all the 4 are adjacent to each other. So minimum we require 4 colors, different colors to color these. Okay. So suppose A I color white, C I will have to color with a different color, right? And D I have to color with a different color. F also I have to color with a different color. Okay. And what about B? So B is adjacent to F and E, right? So I cannot color it red, but it is not adjacent to A or C. So I can give it the same time slot as A or C. So I will give it the green time slot with C. Okay. Now E cannot be colored using green or blue. So it has to be colored with either red or white. So I will color it using white color. So the chromatic number of this graph is equal to 4. Minimum 4 different time slots we have to make to schedule such an exam. This is the minimum. In 3 time slots, we cannot have the exams such that adjacent or there will be clashes in exams. Two students will be having exams for which at the same date and time where he has to appear in both of them. So we need minimum 4 different time slots for this. Okay. Now this is the chromatic number which is telling you about the minimum resources required to conduct the exam following the constraints. Okay. Now let us go to the concept of chromatic polynomial. Okay. So I'll erase everything else. So what is chromatic polynomial? Suppose you don't want the minimum number of time slots. You already know you have, suppose, 8 different time slots to conduct the exam. Okay, you have not 8, let us take 1, 2, 3, 4, 5. 5 colors we have. So let us take, you already have 5 different time slots available to you. Time slots that is available to conduct the exam, and let these 5 different time slots be represented using 5 different colors. Okay, so in how many ways can you conduct the exams, okay, given you already have 5 colors with you, let this 5 be represented by lambda colors. You already have lambda resources. You want to distribute the lambda resources such that no two adjacent nodes have the same color. How many possible ways you can do that? So the first node A can be colored using all any of the 5 lambda colors. Okay, we will assign lambda to it. Then the adjacent nodes to it cannot be colored using the same color, right? It will have one less choice. It will have lambda minus 1 choices. The adjacent to C, it cannot be colored using the same time slot with C and A. So it has lambda minus 2 choices to be colored. F has cannot be colored using A's color, C's colors and D's color. So it has lambda minus 3 choices. What about B? How many choices does B have? It cannot be colored using F. So it has how many choices? Right? Lambda minus 1 choices. And for E, how many choices it have? No, it cannot be colored same as B and D. So it has lambda minus 2 choices. To all possible ways or all possible different assignments that can be time slots that can be given to all these subjects of exam is multiplication of all these possible ways, right? So that would be lambda into lambda minus 1 how many times? 1, 2. 2 times. Lambda minus 2 how many times? Okay, I will write it more neatly. So the chromatic polynomial or number of ways you can conduct the exam using lambda different time slots is lambda into lambda minus 1 square, because we have lambda minus 1 of choice ways and lambda minus 1 ways, 1 lambda minus 2 ways, and lambda minus 3 and lambda minus 4. So this is the chromatic polynomial for the graph, or if you have a certain amount of different time slots which is greater than the minimum time slot, then in how many ways you can use to conduct this exam following the constraints. Okay, so I hope you are clear with the difference between chromatic number and chromatic polynomial for a graph. Please subscribe to my channel and share it with your friends if you like this video, and stay tuned and keep looking in your real world and see where you can apply graph theory in your everyday life. Okay, bye bye, happy learning.